Hey guys, in this video, we're going to explore the basics of writing shaders in GLSL. So first, we're going to see what shaders are, how to set them up in Three.js, how to write GLSL, and then we're going to go through a series of different exercises to create different shapes and patterns. And finally, we're going to create a project, and I'm going to show you the full process of writing a shader from scratch, going from zero to something that looks good. So what are shaders and why do we need them? Well, in 3D graphics, the main thing that we want to do is rendering objects. Now, I might want to render this Rubik's Cube here, or I might want to render a simple sphere. And okay, we want to render the sphere. We want to draw the sphere. And we need to tell the GPU to somehow draw the sphere for us. As you know, the GPU only can draw triangles. So let's draw a triangle here. And okay, we want to draw this triangle with the help of the GPU, and we need to tell the GPU how to actually draw this. So the only pieces of information that the GPU needs is the positions of these vertices. So I'm gonna write positions here, and the other piece of information that our GPU needs is the color of this triangle. And that's essentially what the vertex and the fragment shader do. Now, the vertex shader tells our GPU where these vertices are placed. So I'm gonna write vertex shader here. And the fragment shader tells our GPU how to actually fill this triangle with a color. And okay, that's the basics of what the vertex and the fragment shader do. Now, why do we even need to tell the GPU to draw these triangles for us? Why not tell the CPU? Well, the structure of a CPU is a bit different. You see, I have a CPU with 8 cores and 8 threads. Now, if I want to run multiple tasks at the same time, I can use those 8 threads to run multiple tasks at the same time. Now, the difference is the GPU has hundreds of threads. So the GPU can run hundreds of different tasks at the same time. And okay, we understand that the vertex shader tells our GPU where our vertices are placed, but what is it and how does it really work? Well, a vertex shader is a program that runs for every single vertex. So we have a programming language for this called GLSL. We write this program that is called the vertex shader, and this program runs for every single vertex for our object. And the interesting thing is these vertices have no idea what positions other vertices have. And as I said, the GPU runs this vertex shader in parallel for every single vertex. And okay, now what does the fragment shader do? Well, the fragment shader is very similar, but the fragment shader runs for every single pixel in our triangle. And again, these pixels have no idea what the color of their neighbor pixel is. They just don't have any shared data. So you can imagine that the fragment shader runs for every single pixel and tries to fill the color of our triangle, right? So that's the basics of what you need to know about a vertex shader and a fragment shader. And okay, there are a couple of details about how does the vertex shader work with the fragment shader, but we're going to get into that later. So let's see how we can set up a fragment shader and a vertex shader in Three.js. And here inside of VS Code, I have this repo opened, which you can download from a link in the description. And first you need to npm install to install the modules needed to run this. Now, in the terminal, you need to run npm run start to run this. And when you run it, you'll get this, which is a sphere with some lighting. Now, if I go back to VS Code, if I open up the src folder, app.js is where the main stuff happens. So let's open that up. And here at the top, we have some code, which is unimportant. And here I've isolated the code that is actually important. Now, if you're a beginner in Threejs and you know nothing about Three.js, I recommend you watch a video that I've linked in the description for you. So with that being said, we have the main section of this whole thing here. We create an icosahedron geometry, we create a mesh standard material, we create a mesh from those, and we add that mesh to the scene. And we will get this a white icosphere. So The first thing that I want to change is this mesh standard material. So let's do shader material. And when you do that, you'll get this red icosphere. Now, that's already working with shaders. You're already working with shaders. It's just that you haven't provided them to this shader material, and this shader material class is actually using some default shaders. So those default shaders can actually be a good starting point. So let's close this src folder. Let's hop into node modules. Let's scroll down to find 3. So here it is. And in the src folder, scroll down, you're gonna see materials. Click on that, and here down in the materials folder, you'll see shader material.js. So open that up, and here you're gonna see the class of shader material, and you can see the code behind that class. Now, if we scroll down a bit, you're gonna see this piece of code. In the constructor, we have a default vertex and a default fragment shader, and here you can do control click to open it up. So here you're gonna see this shader code, and this might look a bit different for you. Here we're using this comment. Actually, Threejs is using this comment, and we're using an extension called GLSL literal. So you can download that and install it for VS Code. Syntax highlighting for GLSL instead of JavaScript tag template strings. So that's what it does. And with that, you will get this syntax highlighting within VS Code. Now, this is a JS file, of course, and we're exporting this string. So already you can see that shaders are strings. And then we compile these strings, which are written in GLSL, and that's how shaders work. Now, let's open up default.fragment2, and you can see we have the fragment shader, exact same stuff. Of course, the code is different. Now, what we want to do is we want to copy these into some GLSL files, right? So let's copy this bit of code here in the vertex shader. Let's go into app.js, and if you scroll up at the top, I've put some vertex shader and fragment shader files for you. And I've already placed those in the shaders folder, in the src folder of our repo. So if you open that up, control click here, control click, that's gonna open that up. And here you can paste what you just copied from that Threejs JS file. So we're gonna do the same thing for the fragment shader. Come here, just copy it, and in the fragment shader, control click, and paste that in. So that's all. You can see these are GLSL files, and the way that this is handled is we're using the raw loader, and what the raw loader does is it's essentially taking these files and turning them into text and strings. So we're gonna come down here in the shader material section. We're gonna pass down an object, and we're gonna do vertex shader equals vertex shader. Same thing for the fragment shader. Fragment shader equals fragment shader. And you're gonna see the exact same thing because we just copied some code from Threejs that is there by default. But if we go into this fragment.jlsl, which is where the color of our object is defined, you can see we have this vec4 construct, and what it's doing essentially is this is the red channel, this is the green channel, and this is the blue channel, and this is the alpha channel. So you can see we have the red at 1 and the blue and green are at 0, and we get red, of course. Let's change this to 0. Let's change the green to 1, and as you can see here, we get green, right? It makes sense. So that's all the setup that you need to do in order to run your shaders with Threejs. And now I'm going to explain GLSL here in the fragment shader because it's very easy to visualize things in the fragment shader. All right, so let's close this and this and this. We don't need them anymore. Let's also close this. Let's zoom in a bit. So let's see what's going on in this fragment shader. So first, we see void, and we see something that looks like a function definition, and we're setting this variable to something. All right, that's what we understand if you have a basic understanding of programming languages. Now, right off the bat, you see this void here. So GLSL is a typed language, and if you want to see common types that are used in different programming languages, I'll put a link in the description in case you're interested in that. But here we have a few different types available to us. So we can do float, we can do double, we can do int, we can use, I don't know, uint, things like that, right? But GLSL has some unique types too. So if I come down here, I can use vec3. What does that mean here? Well, if you've used Threejs vector 3, it's kind of similar. What this does is this holds an x and a y and a z. So that's what it does. This is, by the way, not syntax, correct syntax. I need to comment these. So a vec3 holds an x, y, and z. We also have a vec2, which holds an x, y. So you start to understand what's happening, but what are these x and y values? Well, when you use a vec2 or a vec3 or a vec4, which are available, vec5 is not available. When you use those, you're actually storing floats. Okay, so you're storing floating points in these constructs. Now, if I comment these, I can come down here and I can do ivec3. If you want to hold x, y, and z, but you want them to be an int, you use ivec3. uvec3 also exists. You also have boolean up there, bool. You can see it's getting highlighted. You also have bvec2, for example, and so on. So you can have also dvec2, dvec3, double. And yeah, these are all things you could use in GLSL. So these are the types that GLSL has by default. Now, okay, that's cool. But how do we actually define a variable in GLSL? Well, let's come down here, and what's happening here is we are setting this variable to a vec4. So these are all floating points, and here, if we want to take this, we can do vec4, I don't know, color equals this. Put a semicolon there. Now, we're setting this color to this vec4, and you need to specify the type at the beginning and the variable name. And here we can set this variable again to color. That works. And we get our green sphere. So, that's very simple stuff that you can do. Now, let me show you one thing you can do with these constructors. So I have this vec4 constructor, which takes 4 floats. Now, the cool thing is that I can pass only one float. So if I do 1 here, what happens here is we get white. And that's because for every single component, x, y, z, w, that's the 4th component, it's setting all of those to 1, right? So that's one thing you could do. Another thing you could do is use a vec2 for the x, y. Like you can do vec2 1 and 1, and you can also do vec2 1 and 1. That also works, and you can see we get our white sphere. Right, so you can do 2 vec2s, and what this represents is 2 xy's, which will be the xy of this, and the other 2 components here will define the z and the w. All right, you can also do vec3 and put the 1 here, and you can also do a single 1, right? So because this is a vec3, it holds 3 components. We need vec4, we need to add 1 more component here at the end, which is a floating point. So you can do all of that. That works. If I make a mistake here, for example, if I remove this semicolon, we'll get an error because shares get compiled. If I go into my console, if I zoom this in, you can see we get our error. It's saying syntax error. All right, so this gets compiled, and if I make a mistake, this doesn't compile actually. So that's all very simple. Let's set this to green again. So put this at 0 and put this at 0, and you'll get green again, right? So now you know how to work with these types, how to create a variable, and you can also do float green value, for example. I'm just showing this as an example, and come here and say green value, right? That works. Now, one thing that you might have realized is that if I come here and create a vector, call it my vector equals, and use a vec3 constructor, if I use an int here, this is fine. This works, right? The reason for that is this constructor considers ints too. So it takes into account that this is an int, it converts it into a float, and it sets all of those components x, y, and z to 1. And I can prove this, and here I can do vector, my vector dot x, set the x value of this vector to 0. This is an int, this is not a float, and this gives me an error. Why? Because I haven't converted my 0 to a float. The way I would do that is I put a dot here. That works. It's the same as essentially a dot 0. I can remove the 0. This also works, right? So here I'm trying to explain different things all at once. Now the other thing is, I think you can also do f here if you want to. 0.f means float. That compiles fine. I can do 1 here and so on, right? So this f means I'm converting your number here to a float, and that all works fine. Now here's the thing that you can do in GLSL. For example, in JavaScript you have classes. In GLSL you have structs. So I can do struct, and I can call my struct, I don't know, vec5. Because why not? GLSL doesn't provide that. Now it's important to put a semicolon here after the curly brackets. And here I can specify my components of the struct. So I can do float x, float y, float z, float w, and finally float q. And the way that this would work is I can come down here and do vec5, my vector, and what I can do is I can do equals vec5, which is a constructor, and I can give it, this time I can't just give it an int, because that's not a native struct in GLSL. I need to provide all the components. So if I do 1, 1, 1, 1, 1, give it 5 components, this is not going to work because I need to convert all of these to floats. And if I do that, that works. That compiles fine. So that's how that works. You can define functions. So the same way that we have this main function, we can define our own functions. So we can do void do nothing. And this is the way that we define a function. It returns nothing, it takes nothing. Let's change that. Let's change that to sum. Let's do float. And here I can take float a, float b, and return a plus b. And this is compiling fine. And finally here I can do, instead of this green value, I can do sum of 0.5 and 0.5. And this should work the exact same way as before. So here I want to explain swizzle masks, and the name is a bit weird, but the concept is very simple. So here in the main function, I'm going to define a vector. So vec3, and we're going to get my vector equals vec3 1 0 1. And if I call this color, I can also call this color. So we can put a vec3 here, as I just showed you. We can do a vec3, and with a vec4 constructor, this is gonna give us a vec4. So this will give us purple, I believe. Yep. So now we want to set this color.x to 0. Remember, if we do an int, it doesn't work. It gives you an error because we need to convert this into a float. Now, this is one way of converting things to a float, either putting a dot and f after that, or putting a dot and a 0. The other way is taking the int and wrapping it like this around this float constructor. And this also casts it to float. Alright, I don't really use this that much. I just rather use the simple 0.0. Okay, that gives us blue because we're setting the color here to the red color here to 0. Now the thing is, we're modifying the x, but in GLSL, x, y, z, w are the same as RGBA, right? So I can do R here also, representing the red, and it works. So color.x equals .0. These two lines are the same, right? Because RGBA is the same as XYZ. Now, I want to explain swizzle masks. So what are swizzle masks and how can we use them? Well, what if I wanted to modify R and G at the same time? So in order to do that, you might do something like RG, you know, put this as 1 or something. You could do that, but GLSL gives you a convenient way to do this. You can do RG. So if you do RG, you need to provide a vec2 here. Remember, you need to provide 2 floats because this is 2 components. And here we can do, for example, I don't know, whatever the vec2 constructor allows. I can do 0, 1. So what that does is this puts the OR at 0, and this will make the green value 1. So this gives us a cyan color because the green and the blue are 1. Let's change this to purple again. So you can do that if you really want to. Now, the thing here is that you don't need to do this in order. You can do GR, green, red. This also works. So we just reverse this and this. You can also do GRB. That also works, but here you need to provide a vec3 now. So you can do it like this, and this should give you a green value because you're setting the green to 1, the red and the blue to 0. So this gives you a green value. All right, so we understand that, and this is the exact same thing as y, I don't know, x, z. And here's the thing though. So the thing that you need to be careful about is that you can't do XR. That doesn't work. Or XR, I don't know, G. You know, you can't use XYZ with RGB. That doesn't work, right? So you can either do XYZ or RGB together. So that's a swizzle mask. Now, if we remove this, you can see we have this color, and this is supposed to give us a purple color. Now, here I can use the swizzle mask this time like this. I can do X, X, X. And what this gives us is this gives us a vec3, right? So I have a vec3 here and a float, which is a vec4. And this will give us white. Why? Because, well, the red value here is set to 1. So we're essentially, what this means here is that we're doing this 1, 1, 1, and this gives us a white color, right? So you can use swizzle mask like this. You can do XX, I don't know, Y at the end, and this gives you a yellow color. So there you go. That's essentially what swizzle masks are. They're very useful. I don't know any other language that is capable of doing swizzle masks. And now let's talk about some basic operators that you could use. We already saw the equals operator. You can also do color.vec3. That's also possible. So you saw this. One other thing we could do is we could use the plus equals operator. So if I set this to 0, set this to 0, and if I put, I don't know, 0, 0, 1 here, this should give us blue. And if I remove this, this will give us blue. So you can do plus equals, you can do minus equals, you can do multiply equals, and that does work, but here we're multiplying everything by 0, so it doesn't show us anything. If I turn this to 1, this will give us something. There we go. And the other thing we could do is divide equals. That's also available. So you have all these operators. You can do vec3, I don't know, my vector, and color divided by vec, you know, color.xx divided by vec2, because we're getting 2 components. And we can do 2 and 2 here. We need to change this to a vec2. This will work. It will compile fine. So you can do all sorts of crazy things with GLSL. Now, one thing you cannot do is you cannot do color.r mod. The mod operator doesn't exist in GLSL. So the way that you would do mod in GLSL is using the mod function. All right, so we're gonna get into functions and how to use them next, but for now we're gonna delete that. So if you do, I don't know, color.x, you know, mod equals, or even mod alone. Let's just create a new float. New float equals this. For example, if you do 2, this doesn't work. This doesn't work because we don't have mod in GLSL. And here you can see mod, wrong operand types, no operation, mod exists, that takes a left hand, blah blah blah. Right, so this doesn't exist, but we could do mod color.x 2. We could do that. So if we take a look, let's see what's the problem. I think I need to provide a float here for it to take that. Yeah. So mod works like this. All right. So now let's talk about the different math functions that are available, like mod in GLSL, because GLSL has a lot of math functions that are very useful. So we're gonna just cover the basic ones here, and some of the functions in GLSL we're gonna cover later in this video, but I'm just gonna cover the basic ones. So you can use abs. What that gives you is the absolute value of a number. So you can do min, you can do max. These are all valid functions in GLSL. You provide two values to these, and the min gives you the minimum value between those, and the max gives you the maximum value out of those two values. So basic functions here. What else? You have mod, which I just talked about. You have sine, you have cosine. You also have tan, I think. Let's check that out. Yep, you have that. You have atan and things like that. You have all sorts of math functions that you could use. Now, these are some of the basic ones. What else do we have? We have the dot product. We have the cross product. These are both functions that you could use. So yeah, we have many of these, and we will use these functions in the future. One interesting function that I pretty much always use in all of my projects is the clamp function. This is very important. The clamp function, what it does is you give it a number. For example, I give it minus 0.1, I don't know, and you can clamp it to fit a certain range. So if the number goes below this min value, it gets converted to the min value. So here, this is minus 0.1. This will get converted to 0. Now, if you go above 1, for example, here, which is the maximum value, if you go above 1, put 2 here, this will again be 1. But if you go in between, this will return the value itself. So this is a very useful function that we're going to work with later. And you have also some math functions that you might not be familiar with, but these are super important. So you have step, you have smooth step, you have fract, and so on. And we're going to cover these later. I'm not going to tell you what they do now. We're going to cover these later down the line. Now, a very interesting function that I found out about recently was this equal function. So here you can do whatever you want with your types, but for example, if we go for a vec3, we can do bvec3 and say, okay, is equal, and we need to now do equal, and we can provide two vec3s here. So this checks if two vec3s are equal, and it will check those components individually, and it will return a bvec3. So I can provide a vec3 here, one with 1, one with 0, and all the numbers here should be all the booleans here in this bvec3 should be false, right? Because these two vec3s are not equal in any component. So if I come here and say is equal, if we try to visualize this, remember booleans can only be true or false. So this is all false, and false in this programming language is, like many other languages, 0. So if we now take a look, we're gonna get a black screen. We don't get any error, but this is a black. Now if I change this to 1, you will see this will be equal, and we will get white, right? And you know, take a look at this constructor. This is a vec4, and it takes a bvec3 here, and it turns it into a vec3, or essentially it takes all the components and turns it into floats, and this will provide the full vec4 like this. So that's very interesting. Some of these things you cannot really do in other programming languages. So GLSL is really fun to work with. And that's the basics of what you need to know from GLSL. As I said, there are some functions that are very useful, which you can use. And we're going to talk about those later in this video. But for now, that's all that you need to know about GLSL. Alright, so now let's delete all of this code. So we're going to delete this, we're gonna delete all of this code, and you can see the fragment here is a very simple program, and we can define everything with just 3 lines of code. So let's turn this back to red, and if we do that, we get our red sphere. So that's all nice, but okay, we now understand how the fragment here works. We have this main function, and we set this global variable GLFragColor, which determines the fragment color to red, and we get red. That all makes sense. But now, how does the vertex shader work? So let's take a look at the vertex shader. If I click here, you're gonna see again, we get 3 lines of code, very simple. But here again, okay, we have void main. That makes sense. We have the GL position, which defines the position of the vertices, as we discussed. That also makes sense. And this is a global variable again. That also makes sense. But here we have 3 different keywords that we have no idea what they are. So we have projection matrix multiplied by model view matrix. And we have this position keyword. And you don't see the definition of these here in this file, and that's because Three.js shader material class already creates these for you. So in order for me to explain what's happening here, we need to take a step back and we need to define these ourselves. So if I go into app.js, let's change this to a raw shader material. And the difference between a raw shader material class and the shader material class is that the raw shader material doesn't have that boilerplate code that Threejs already does. This will crash with our current shader setup. And as you can see here, we get projection matrix undeclared identifier. It means we haven't declared this variable. Also model view matrix, we haven't declared that also. And the position also is undeclared, right? So again, those three things that we saw, we now need to actually specify and we need to actually create them. So if I go back into vertex.glsl, let's see what the error suggests. So we get this error. It says projection matrix undeclared identifier. Let's copy paste this name, projection matrix. So it seems like this is a matrix. And okay, what is this? So follow with me. Type in uniform matrix 4 mat4 and projection matrix. So this is a uniform, and we're gonna talk about what's that in just a second. But if we reload the page, you can see the error message for the projection matrix is gone. Let's do the same thing for this model view matrix. So we have a uniform mate mat3 and model view matrix. And if you reload the page, the error for model view matrix is gone. Let's copy this position. And this time, instead of doing a uniform, you can actually see here that this vec4 is being constructed. And this position, we don't know what this is, but we know that this vec4 needs 4 components. One is provided here, so this needs to be a vec3, right? So we know that. What is this exactly? So the position here is actually an attribute, and I'm going to explain what that is, but for now, let's just do attribute vec3 position, semicolon. And this is going to work, and we're going to get our red shader back. But okay, now, what are these attributes and uniforms? What are these exactly? So far, we've been just kind of focused on the GLSL side of things, the shader side of things, but JavaScript and Threejs need to communicate with shaders, right? So we need to send data to shaders. And if you remember our triangle example, for each vertex in the triangle, we need to actually know the position and we need to send that to the vertex shader. So that's what we're doing here. We're sending data from JavaScript to this vertex shader, and we're sending this vec3 position thing. Now, what is exactly an attribute? If we go into app.js and if I come down here below the geometry, if I console log geometry, if we take a look at the console, you're going to see we get this geometry, and the first parameter here, the first property is this attributes object. If we open that up, you're going to see we have a few different properties. We have the normal, we have the UV, and we have the position, right? And I'm going to explain normals and UVs later, but for now, let's focus on this positions array. And this is an array because you can see this is float32 buffer attribute type, and if you open that up, you get this array. If you open the array, this is just a JavaScript array, and what this is doing is it's defining the coordinates of our triangle points to construct the sphere, right? So that's what this array of positions is doing, and we're sending this array to the vertex shader, and the vertex shader is able to draw our triangles. Now, if you take a look at this item size property, you can see this is 3, and you can see we have an array of floats, right? So when you have a float, when you have 3 floats, what would that be? It would be a vec3. So that's how this all works together. we have an attribute and it's a vec3 and we call it position. Now the same name here is applied. We have position, and this is important because when you add an attribute in Three.js, Three.js creates an attribute on the GLSL side of things, which you can use like this. So that all makes sense also, but now what are these uniforms? What's the difference between a uniform and you know, an attribute? And you can see here, this is a type that I haven't explained, so I'm going to explain it very quickly here. You have a matrix type, and this is mate4. This is a 4x4 matrix. So a mate2, for example, will be like this. You have this structure exactly like a matrix, for example. And it's just like an array, but it's of course a matrix, and GLSL provides some math to actually deal with these. Now you can actually do math to x and 2 again, and this would be the same thing because the mat2 was actually a square matrix. So you can do this. You can also do mat2 x3, which is a 2x3 matrix, and so on. So that's a quick explanation of this mat4 type. But here we have this uniform thing here. So what does that mean here? Now, if you look into the geometry, can we see a uniform here? If you look through it, you don't see any uniforms. So what is this uniform and where is it coming from? So let's go back here, and instead of logging the geometry this time, let's console.log the material. And when you do that, you get a raw shader material. And if you scroll down, you're gonna get this object that is called uniforms. And right now it's empty. Why is that the case? Well, the problem is Threejs creates these uniforms for us, and we can't actually see it in the raw shader material. Here I'm going to explain the difference between attributes and uniforms. So as you saw, attributes was this huge array of positions, and for each vertex we have a specific data, right? So attributes are essentially vertex specific data that we're storing in an array, right? So for each vertex we have a specific data. That makes sense. Uniforms, on the other hand, are a bit different. So if I come down here and I do material.uniforms, and I create just a new uniform, let's call it time, for example. Let's just do that. I need to do equals, and I create an object. And here what you need to do for uniforms in JavaScript is provide a value property. So you're going to do value, and let's set this to 0 by default. Now if you console.log material, if you go into the uniforms, you can see we have this time with the value of 0. That makes sense. Now if you want to access this uniform, you're going to come down here. You're going to do uniform float time. I misspelled here, uniform. All right, and this works. You get time in your shader. So that's essentially what Threejs is doing in the background with these uniforms. It's just passing them in through the material. Now the difference here is that the uniform is the same for every single vertex. And that's a huge difference because for positions, we have different positions for each vertex, and it's specific to the vertex that we're currently running this program on. But a uniform is the same across all the vertices. And a uniform can also be used in the fragment shader. So you can come here and add uniform float time, and that will work perfectly fine. But here we have a problem. So if you look at this error, it says error, no precision specified for float. You wouldn't get this error with the shader material class, But with the raw shader material class, you need to specify a precision for floats. So let's do precision, and then you need to specify the precision. So we're going to do medium P and float, semicolon. And that specifies the precision of your floating points. And we'll get our shader, which compiles fine. So you can also use uniforms in the fragment shader. But if you, for example, copy paste this attribute and paste it here, this is going to crash. Why? Because attributes are vertex specific data. And here there says attributes supported in vertex shaders only. All right, so you can't use them here. So now that you understand attributes and uniforms and how they work, I want to explain this bit of code here, which is the math that is essentially happening in our vertex shader, and then you'll be able to understand how this vertex shader works. Alright, so the first thing that you need to know is that this model view matrix is actually two matrices. So one matrix is uniform mat4 model matrix, and the other one is, you guessed it, uniform mat4 the view matrix. And I want to explain what these are in a bit, but here we can do view matrix multiplied by model matrix. And this gives us the exact same result. You can see our shader compiles just fine. And okay, so what are these exactly? So let me zoom out a bit so you can see the full line here. So I'm going to explain these. Now I'm going to use a term called transform. And what transform means is we're talking about the position, the scale, and the rotation. All right. Now, for example, the model matrix provides the transform of our model, and the view matrix provides the transform of our camera. That makes sense, right? So let me write this down here. Model matrix is essentially the position, scale, and rotation information of our model, right? And the view matrix gives us the position and the orientation of our camera. And the projection matrix projects our object onto the screen, and it takes into account the aspect ratio and the perspective. So we have these three matrices and we multiply them like this, and the order here matters. So this is often called the MVP, model view projection matrices, but the order is actually in reverse. So first you need to write the projection matrix multiplied by the view matrix multiplied by the model matrix, and finally multiplied by the position. All right, so that's all that there is to it, and with that we're gonna get this. Now if you, for example, I don't know, remove the view matrix, you're not taking into account the camera position and orientation, so now the camera is right at 0, and I can prove that to you by moving our object. So we can come here and we can set ico.position.set, and we can set this to 0, 0, -5, and we're gonna see our object, but we cannot move the camera anymore because we're not taking into consideration the camera's position and orientation. So that's all that there is to it. And as I said, you cannot change the order of these. For example, if I take this and if I paste it, for example, here, you're gonna get some weird results because this is not gonna work. But if I turn this back to where it's supposed to be, we're gonna get our object right here. Alright, so now that we understand what's going on here, let's clean this up a bit. So we can remove all of this code, and I can come here and cut all of this until the very end. We can create a vec4, call it model view position, and paste the whole thing here. And here, if you remember, we can replace this with model view matrix. So that's all we need. And we can cut this too and create a new vec4 called projected position equals this multiplied by model view position. All right. So, and finally, GL position is equals projected position, right? And this will give us the exact same result as before. And let's go back to the shader material class so we can remove all of this code. Let's keep UTime here because that's our custom uniform. Let's remove this line too, precision float. And let's keep UTime, and let's go into app.js, change this to shader material. And this should give us again the exact same result as before. Now, to explain some things, first let's go back here, and if you remember, we had an attributes object within the geometry. So let's console.log geometry.attributes, and when we do that, we get something in the console. We get an object, and we have the positions and the UVs and the normals here. Now, what are the positions? We already discussed. This is the position of our vertices for this icosphere. I'm gonna here briefly explain what the normals and the UVs are. So the normals are the orientation of an object at a certain point. So for each vertex, we have a normal, right? And this is a vec3, and a normal is a vec3. And this gives us the orientation of that vertex on the surface of our object. Does that make sense? I hope it does. So that's normals, and we're gonna get into how we can use them in the vertex shader later. So next we have UVs, and if you open this up, if you open up the normals too, you can see the item size for the normals is 3. So this is a vec3, and of course this is a float array. So that's how you know this is a vec3. And again, if you open up the UVs, this is a float array, but the item size here is 2. So UVs are vec2s. And what are UVs or UV coordinates? Well, when we want to project a texture on our object, for example, on our sphere here, we use the UV coordinates to do that. And UVs are just coordinates in the 2D space, and we can just map a texture to our object. So that's what the UVs are used for. All right, now let's go back to some drawings that we had earlier, and let's recap what we have learned so far. So we know that in order to render things, we use triangles, and in order to tell the GPU how to draw the triangles that we want, we use the vertex shader and the fragment shader. Now, the vertex shader tells the GPU where the position of our vertices are, and the fragment shader tells the GPU how to fill our triangle. So we already know that, but we also learned some new things. So one thing that we learned is that we have a layer of JavaScript, and we control our application with JavaScript. So let's write that down. And when we want to send information from JavaScript to the vertex shader, we use attributes. So let's write that down. And we know that we could also use uniforms to send data to our shaders. So let's write that down too. And the difference between attributes and uniforms is that the attributes are vertex specific, but uniforms aren't vertex specific. And we also know that attributes are used in vertex shaders only. So only vertex shaders can access the attributes. But the vertex shader and the fragment shader can both use uniforms. All right, this is the bigger picture of the whole thing. The problem is our sphere that we have right here is flat and boring, right? There's no depth. It doesn't really seem that this is a 3D sphere. It looks like a circle. The problem is we cannot send direct information from JavaScript to the fragment shader. I mean, we can, but we can only send uniforms, which are global variables. Now, the key piece that is missing here is the communication between the vertex shader and the fragment shader. So next, let's talk about how vertex shaders and fragment shaders communicate. So we already had attributes, we already had uniforms, and we have another type of variable in shaders, which is called varyings. Varyings are used to send vertex data from the vertex shader to the fragment shader. So this all now makes sense, right? We have this thing that is called varying. All right, that makes sense. And that's how we communicate. But if we go back just a bit, let's talk about this a little bit. So if we want to send vertex information from the vertex shader to the fragment shader, this kind of doesn't make any sense, because if you remember this triangle that we have 3 vertices here, right? But within this triangle that we want to render, we might have hundreds, thousands, or millions of pixels. So how can we send data from 3 vertices to all of these pixels? And you might already start to imagine how this will look like, but the best way to explain this is by showing you. So let me go back into code very quickly here. And if we go into the vertex shader, again, remember we can send data from the vertex shader to the fragment shader. So we can come down here and define this varying. Let's call it varying. And let's define this as, I don't know, vec3. Let's pass in the position. So we're going to call it v position. This is the convention. You put a v behind it and you write it in camel case. So the same thing with the uniform. So you can do u plus time. And the way that you will send information from the vertex shader to fragment shader is like so. You do v position equals position. You just assign it to a variable in the vertex shader, and in the fragment shader we're gonna copy the exact same line that we have here, and we're gonna paste this in, and here we can visualize how this vec3 will look like. So we can come here, and instead of providing 3 components, we can do v position. All right, and with this you're gonna get this very cool result, and it kind of looks like our sphere is now colorful, and we can actually rotate it to see what's happening. And this is now where the fun part starts. So now for me to demonstrate some things, let's change this icosahedron geometry to a plane geometry. All right, so let's do 1 and 1, and that's the only thing we need to construct this plane, and we get this plane, right? Let's close this and let's zoom in a bit. So what's happening here is that our fragment shader is taking the position at every single point and it's displaying it as a color. So let's imagine what values we are sending from the vertex shader to the fragment shader. Now, as you know, we're sending the positions, right? So let's think about this point here. This is definitely a vertex, and we can view this in wireframe mode to confirm that. So I can set wireframe to true here, and we will get a wireframe. And you can see this is a vertex, and we have 2 triangles here, right? One is this one, and one is this one. Now, what's happening here, if we comment this out, is let's take a look at this, right? What's the position? What's the world coordinates that we have for this point? So our plane is 1 by 1. What this means is this whole section is 1 unit and this whole section is 1 unit. Now we can make it 2 to make this whole section go from 0 here at the center to 1, right? So let's change this to 2. And this gives us a much better result. Now you can imagine that this is the 0 position in our world, because our plane is positioned as 0, 0, 0, x, y, and z. And as we start to move up, what we're gonna see is we're gonna reach 1, 1. And we're gonna reach 1, 1 in the x and y directions, right? we're not making any changes in the z direction. So the z direction here is actually 0. All right. And what's happening here is we're showcasing this as a color. So what is the color with the xy of 1 and the z of 0? So if we go into the fragment shader, we can visualize that. We can do a vec3, and let's put this both at 1 and this at 0. That's what we're getting essentially. We get yellow. That's why we are getting yellow here at the top. And fragment shaders don't understand the values below 0. So what's happening here with this dark area is that the positions here are getting negative. So what's happening here is GLSL just clamps this to 0. So any value below 0 will get clamped to 0. All right, and we're getting black. We can visualize that even. If we put vec3 0 0 0, of course we're gonna get black, right? So that's how all of this works, and the same applies to the red parts and the green parts. Here at the top, the position in the y coordinates is 1, so we get maximum green, and the red, which is the x, is actually -1. So -1 gets clamped to 0. So we have 1, we have 0 as the red, we have 1 as the green, and the z is also 0 because this is a plane. This is not 3-dimensional, and this is positioned at the z of 0. So we're getting 0, 1, and 0, and that color is green, and so on. So this is how this is working, and we know that we have 2 more attributes as well. We have UVs and normals, so we can come to the vertex shader here, and we can create a new varying vec3 vnormal, and we can come down here and just assign vnormal to normal. Remember, the Threejs already handles our attributes, and we can just use whatever attribute name these are in JavaScript. So here we need to copy this and go into the fragment shader and paste this in. And here let's visualize the vnormals. So what we're gonna see here is a single solid color, and that is because this whole plane, all the points, all the pixels in this plane are pointing this way. Now we're already starting to visualize things, and we don't see the problem that I just discussed while drawing. So we have 4 vertices here for this plane, one here, one here, one here, and one here. And the fragment shader is very smart. It's understanding what color we need to put in these pixels. So I'm going to explain how that's happening next. But first, let's visualize UVs too. So I'm going to come here and I'm going to copy paste this. I'm going to change this to a vec2. We can do VUV, that's the convention. And we can come here and say VUV equals UV. Again, this is provided by Three.js. So we can copy this, go into the fragment shader, paste this in, and here we have the VUVs. So let's visualize this. Now, the problem here is that VUVs are vec2s, so we need to either put it here and provide a value or component here, or we should put it like this and provide a component here at the beginning. I'm going to do it like this because we get the red and green values like this, and it's very easy to explain. So here we can see the UVs. The UVs, I'm going to explain how they work. So they go from 0, 0 here, all the way to 1, 1 here. So from the starting point, they are 0, and they start to transition to 1. And this is 1 in the x coordinates and 0 in the y coordinates. And we're getting red. With that, the opposite is true here. So as we're moving up, the y is 1 here and the x is 0. So we're getting green. And this final point here is 1, 1 for green and red. And of course, the blue is set to 0 here. I can set the blue here to 1, and we will get a slightly different variation. But you can start to see what's happening. Now, here's the cool part about GLSL. As I said, we can do sizzling, and if I put vuv.xxx here, this provides a vec3 with all the components being vuv.x. So what we will get is a value that starts from 0, and as we move to the right, we get 1 here. But this doesn't explain the problem that I just mentioned earlier. So if we go into wireframe mode here, as you can see, we have 4 vertices and 2 triangles, right? Now, how does the fragment shader know what color to put here when I turn off wireframe? As you can see, we get the smooth gradient. So what the fragment shader is doing is interpolation, and we can get into what interpolation is and how it works. And there are many good videos out there about interpolation, and I'm going to put some links in the description in case you're interested to see an in-depth explanation of what interpolation is. But the basic concept here is that if we have 1 point here and we have 1 point here in a one-dimensional space, if we assign a value to this point, and if we assign a value to this point, we can guess the value of the points between these 2 points. That's interpolation. So if this is 1 and if this is 0, we know the middle is 0.5. That's how it works, kind of. And this is also known as lerp, and GLSL provides a function to us to do lerp. So I can go into fragment here. So let's remove this and let's use a lerp function instead. The lerp function in GLSL is actually called mix, right? So we can do a mix, and I can mix between 0 and I can mix between, sorry, this should be a vec3 and a vec3 of 1. And we can mix and lerp between those values 0 and 1 with the vuv.x. So let's use that here. So as you remember, the vuv goes from 0 to 1. From one side of the plane to the other side of the plane. And what we should see here is the exact same results as what we saw with vuv.xxx. So let's go back to vuv.xxx, or you can do r if you're interested. It's going to be the exact same thing. Now, the question that might be popping in your head is, what if we don't want interpolation? What if we want hard edges? And we don't want the fragment shader to guess what value is in between, right? We want the exact value at a pixel, and we want to know, okay, if this pixel is closer to this vertex, we want that exact value for that vertex. We don't want interpolation. So the way that you would work with that is you add a flat before the varying definition. When you add flat, you disable interpolation for that varying, right? So you need to add it here, and you also need to add it behind here in the vertex shader. So, and when you do that, what happens is you get a hard edge. Now, this doesn't work because we only have 4 vertices here. So if I increase the subdivision to, for example, 10 and 10, you're gonna get this hard edge look. So if I change this to 2, you're gonna see a hard edge right in between. Alright, so if you've learned anything new so far, give this video a thumbs up, and definitely let me know in the comments down below if you like this type of long format content, so I can make more of these if you guys like it. And with that being said, let's continue. Alright, so we've been kind of jumping from one topic to another. And I thought that that's the best way for you to start learning the basics. And I know very well that this is a lot to take in. So make sure you give yourself enough rest in between these sections. But perhaps the next chapter of this video is the most important one. Because we're going to get into some functions available in GLSL. And we're going to start to draw some things, all right? And it's important for you to have the correct mindset before watching this section. Now, I know as a beginner, it is very hard to understand how the vertex shader and the fragment shaders work. But the correct mindset here is that, all right, for the fragment shader, we're writing this program, and this program is running for every single pixel in our object. And these pixels don't see each other. So the way that this works is you write an algorithm, and your GPU takes this algorithm and runs it on every single pixel, for example, in the fragment shader. Now, you need to think about that algorithm. When you want to draw something, maybe let's say you want to draw a line across the screen, and we're gonna do that later in this video. But for example, if you were using a JavaScript library or something like that, you would call a draw line function, and the library would take care of that process for you. But here in shaders, you need to think about, okay, what algorithm, what function do I need to use that takes some parameters and gives me back what I want? And again, at first, this can be really hard to understand. And just know that with more experience, you're going to improve and get better and better at this. And all right, so with that being said, let's see what things we can draw in the fragment shader. So here back in VS Code, I have the exact same setup as before. I have this vuv.x that we visualize as a vec3. And we get this because we use the flat keyword here. Let's remove that, and let's see what we get with this. And we get a value that goes from 0 here all the way to 1 here at the very end. And so the correct way to think about this is that on this plane we have an x and a y coordinates. We also have z, but we're not considering that yet. So for each x and y, we're taking the x and we're displaying the x, right? So our inputs are very simple here. Our inputs are x and y, and the result is x. So we're displaying x. And in this case, this is our algorithm that I just talked about. And here we are visualizing that algorithm through this shader. Now, there's a site called Desmos, so you can just search Desmos. And if you go into that website, if you open up the graphing calculator, you can actually visualize this function that we're writing. So you can do y equals x. That's what we're doing. And so if you really zoom in on this, from 0 to 1, because UVs go from left to right, 0 to 1, we're getting this this linear pattern. Now, we can visualize this like this here in this graph, or we can visualize it here in the shader like this. Now, if we go back into code, as you can see, we have this vuv.x as a vec3. So let's change this, for example, to something different. Let's do vuv.x multiplied by vuv.x. And now we need to use a vec3 here. So just wrap this in a constructor like that. And when you go back to our shader setup, you can see we still get a gradient, but it's a bit different. So if I change this up to, if I delete this part and change this back to vuv.x, you can see immediately the difference. And the other way to visualize this difference is here at Desmos, I can write y equals x multiplied by x. And this is the function that we're dealing with. And from 0 to 1, you can see we kind of have a different gradient effect. It starts slowly, and then it speeds up. And both of these meet at 1. And here's the important part of all of this. You don't need to memorize any of these functions. You can just see what shape you're looking for, and you can easily visualize your functions and maybe modify them in different places to get the look that you want, right? So that's all that we're doing here. Now, if I go back into code, we can write this like this, vuv.x multiplied by vuv.x. But essentially what we're doing is, this is essentially vuv.x to the power of 2, right? So we can use the power function in GLSL. You write it like this, pow. And it takes the vuv.x, and you can do to the power of 2. Remember, if this is a float, this also needs to be a float. So if you do this, this will crash let me go back here. This will crash and it will says pow no matching overloaded function found, because you need to actually put a float here, right? So if we go back here, you can see we get the exact same result as before, but now with the power function. All right, so that's understandable. We can do to the power of 3, and you're gonna see we get a slower effect. If I go back to Desmos, we can do y equals x to the power of 3. And again, you can visualize this in Desmos here too. You can see it starts lower than x to the power of 2. But again, these 3 all end in one place. So again, different ways to visualize things. Now, I'm going to introduce you to another function here, and that is the step function. So let's write it down, step, and the first parameter should be the threshold. So we're going to do 0.5 and vuv.x, right? So vuv goes from 0 to 1. Let's see what happens here. And what we're going to get is like this. So we have 0 here all the way, and we have all the pixels here are 1. Now, why is that the case? We're going to find out. But first, this area is fully 0, and it's the same as the background color. So let's change that very quickly. Let's open up the file explorer, and let's go here into render init, and we can change the background color here. So we can come here and say renderer dot set clear color. That's what you need to do. And we need to set a hex here. So, and I can do 0x000, and this gives us a black, but I think I have an extension to edit this. So I can come here and I can change the background to be slightly bluish. Yeah, that's fine. Let's change that here and add a 0x. All right, we don't need this anymore. This should work fine. So let's go back, and yeah, our background is now bluish. And okay, this step function gives us a hard edge. And if you're interested in seeing what the implementation of this function is, you can write step in GLSL in Google. And 2 websites show up. One is the Chronos website, which is the official OpenGL website. And the other one is the Book of Shaders. Now, the Book of Shaders is a website created by some developers. And it's a fantastic website for learning shaders. So let's click on that and let's see what the implementation is. And it gives you some declarations here, and we have the description here. And here's the thing, this gives you a step-like shape, right? It goes like this and this. Now, what is this function doing? Well, if we go here, if you wanted to write this in JavaScript, you would write it like this. So you take the edge and you say, okay, if this value, vuv.x, is greater or equals than this edge, we're going to return 1. Otherwise, we're going to return 0. This is how you would write this in JavaScript. And so the values that are below 0.5 are going to all be 0. And the values that are above 0.5 are all going to be 1, right? That makes sense. So that's the step function. Now, you have a similar function to step, which is called the smooth step. And the smooth step is a bit different, but let's take a look at what it does. So you can write smooth step, and here you need to provide, let me just delete this. Here you need to provide 3 parameters. So the first one is the minimum that you want to smooth step. So we're gonna do 0.45 here, and the maximum we're gonna set it to 0.55. And here you can see that I've tried to kind of keep the values around 0.5, the same as we had before with the step function. And here you can provide vuv.x. And if we take a look at the pattern now, this is a smooth step. This is like a step, but it's smooth. Now, this is not exactly how you should be using this function, because the implementation of this is a bit different. So if I come here into the Book of Shaders, let's create a new tab, the Book of Shaders smooth step. Let's search that up and click on this. And if we scroll down, you can see the shape of this function is like a step, but it's smooth, right? So that's exactly what we're dealing with. And here in this website, you can actually change these values. So here we have our smooth step function. We can change this min value to move forward, which is what we did. We put this at this and this. So you can see the effect that it has here. Now all you need to understand is how this function actually looks like. So if we scroll up in the description here, we have the function definition. So you can see the algorithm behind this function. And it's a bit weird, so you don't need to memorize it. Just memorize how it looks. It looks like this. So, okay, now that we understand smooth step, let's move on to the next function. The next function that I want to talk about is length. And length gives you the length of a vector. So if you provide VUV, which is a vec2, you're going to get a slightly different result. Now, this is starting at 0 here. And as we're moving away from 0, 0 here, we're trying to reach 1. And here we're reaching 1, right? So actually what we can do here is create our own UV variable. So we can do vec2 UV VUV, and we can modify this UV now. And you really cannot modify VUV itself. For example, if you do VUV equals vec2 something, this is not going to work because varyings cannot be modified from the fragment shader. So this is going to crash. And yeah, you cannot modify a varying. So let's remove this. But if you store it in a new variable, you can now modify the new variable. So what you can do here is we can change the UVs. So right now, if I comment this out, right now the UVs go from 0 to 1 here, 0 to 1 here, and we have 1, 1 here, right? What we want is we want to move this black point to the center point here, okay? To get a circle-like shape. And I'll show you what I mean. Here, it's very easy to do. So we can do UV plus equals vec2. And all we have to provide is 0.5. So if we add 0.5 to the x and a y, it's going to move up. And if we use this now as the input, we're going to get a weird result. We wanted the black dot to be in the middle, but it's not. So we might be making a mistake here. Let's modify this to minus equals. And there we go. So sometimes you need to experiment with your math. And of course, the reason behind this is obvious. Yeah, sometimes you might forget how to actually do stuff, and you experiment until you get the right result. So maybe we can multiply UVs by 2 and see what's happening. And there we go. So now it goes from 0 all the way to the -1 and -1, x and y, and the same here, and the same here, and the same here. And now we're getting this circle-like, disc-like shape, and we can now use some of these functions together. So if we use a step for this function, remember we need to provide an edge. So let's do 0.5. We're gonna get a hard edge. So if I want to modify the radius of the circle, if I increase this value, we get a bigger circle. So we can create a const float. We also have const in GLSL, so we can do const float radius equals 0.8, and here we can come here and say radius. And the convention is for constant values, you're going to use uppercase letters. So with that, you're going to get the exact same result, and we can now modify this however we want. Now, something that we could do here is we could use a uniform to change this radius All right. So let's make this a uniform. So let's change this back to U radius now. Let's create a uniform here at the top. Uniform float U radius. And we can come to app.js and create a material.uniforms.uRadius. We can create an object with the value of 0.5, for example. And here we have access to this GUI class. So what we can do here is we can add GUI.add. And what we want to add is material.uniforms.uRadius. And what we want to change here is the value parameter. So if we add that, we're going to get a value parameter here. And here we can change this value. So we can do 0.8. We can do 0.9. We can do 2. And this gives us a full black screen. So we can do 0.1. We get a small little circle here. And you can see how we can use this to create different things. So let's make a range out of this. Let's put the min at 0 and dot max at 1. And this is going to give us a range to work with. So you can change the radius like this. And as you can see here in the fragment shader, we're designing an algorithm to draw a sphere. So very simple stuff. Now, some people will tell you that it's okay if you're not good at math in shaders. And I don't really agree with that, because all we're dealing with here are mathematical algorithms. And this gives you so much power, but you also need to be good at math. Now, you don't need to be good at math from the start. I definitely wasn't good at math when I started learning shaders. But you have to always keep in mind that you need to improve your math skills, and you're going to highly benefit from knowing math when it comes to working with shaders. And again, if you're interested in learning the implementation of the length function, you can just search that. And let's go into this Chronos website this time. And this description gives you a full explanation of the algorithm. So length returns the length of the vector. In other words, this mathematical formula. So now this type of writing things reminds me of something. So if we go back here in GLSL, you also have another option that you can use. You can do, to access UV.x, you can do UV and treat it as an array. So the first item, you can get that and set that to, for example, I don't know, whatever, 0.1, and this will compile, and this will of course change the result, but this will compile fine because this is valid in GLSL. You can also do UV, treat it like an array 1. This is UV.y. So this is also available in GLSL. All right, so the next function that I want to talk about is the fract function. So let's remove all of this. Let's just copy it here, and we can comment it like this. And here we need 2 parentheses. All right, so here I want to talk about the fract function. You have a function in GLSL called fract, and you pass in vuv.x as always. Wrap this in a vec3 constructor. Now this fract function is very interesting. What it does is, if you have a number, let's say, let me expand this a bit. Let's say you have a number, and let's say that number is 0.5 or 2.5. What the fract function does is it only gives you back the decimal. All right, so in this case, it just forgets the 2 and it gives you back 0.5. If you had 3.5, it will also give you 0.5. All right, so you can see when it goes up to 1, it restarts 1 by 1. It keeps restarting. So if you take a look at this For example, if you search fract GLSL, if you take a look at the shape of this function, here we have the Book of Shares article. The shape of this function is like this. It goes up and it goes down. It goes up, it goes down. It goes up, and it's creating this spike-like shape like this. The reason that this is not showing anything is because we're only in the 0 to 1 range with our VUVs. So let's change that. Let's come here and multiply VUV.x with 10. And here what's going to happen is VUV.x now goes from 0 to 10, right? So if you multiply the range by a number, both the min and max of that range will be multiplied by that number. So our range here for VUV.x is from 0 to 1. So let me write that down here. When you multiply this by 10, what you will get is you will get 0 again, because 0 multiplied by 10 will be 0, and 10, right? So now you're getting this range for the domain of this function, all right? And you're gonna get this. And if you take a look at the graph, it goes up, it goes down, it goes up, it goes down, it goes up, it goes down, and we're getting the exact same thing here. All right, so now you're getting these stripes here, and if you really want clear-cut stripes with hard edges, what function would you use? Whenever you want hard edges, you pretty much always use the step function. So let's first of all comment this so that we have it, and we don't need these anymore. Let's again copy this. So we're gonna come here and say, okay, step applied to this function. We can do 0.5 again, and if we wrap this around the step, you're gonna get stripes with hard edges. Now, another function which you could use instead of fract is mod. Now, mod, as I described, does not exist like this in GLSL. You need to actually use the mod function. So we can come here and instead of fract, we can do mod, because it does a similar thing. Mod of 1 is fract. So fract, when it goes up to 1, it restarts. And the mod here is the exact same thing, but you can change that parameter. It can go up to 2 and restart. It can go up to 2 and restart. All right, so that's how this works. Now, we can set this to 1 and we're gonna get the exact same thing as before. We can set this to 2 and you're gonna get a slightly different result, of course. And you can also go 3, 4, 5. You can increase the number. And this is very cool, right? So you have full control over what functions you can use and what pattern you can create with these. Now we're gonna use this mod function later in this video to create that final animation I showed you in the beginning. So this is very cool. Let's keep all of this in one comment. Now the next function that I want to talk about is a mix, and this is also known as lerp. Now there are many videos on lerp, so I recommend you go ahead and watch a few different videos on lerp itself, because it's a very useful concept in 3D graphics in general. But here we can do 0.5 up to 1, and what this will do is whatever we provide, it will lerp from 0.5 to 1. So we can provide VUV.x. And what happens here is this is going from 0.5 at the very left here all the way to 1. And we can change this range. We can do 0 to 0.5. So the reverse of that, kind of. And here we're going to get 0 at the very left and 0.5 at the very right, right? So this is how this function works. Now this also works for vec3s, vec2s, etc. But I thought I just introduced this to you, and this can have its own video, honestly. So make sure to do your own research on lerp. it's a very useful concept in 3D graphics. Now, I will not explain it because if I wanted to explain these things, this video would be 10 hours. Okay, so the next function that I want to talk about is the dot product. So let's cut this, paste it here. And for the dot product, I'm going to explain the algorithm because it's a really important function. So the dot product is written like this. It's a function in GLSL, and it takes two vectors. So it takes vector A and vector B. Let's define these here at the top. So I can define a vec3. Let's call it vector A equals vec3, maybe 1, and let's define vector B. Let's put this as 0. And what the dot product does is very simple. The dot product gives us a single value at the end. So we can do float dot product. Let's just call the variable that. So here I can input these, vector A and vector B, and this should run if I put the dot product here to visualize it. This should work fine. Now we're getting a value. Now, what is this dot product doing exactly? So the algorithm behind dot product is like this. You take vector A dot x, you multiply it by vector B dot x, you add it to vector A dot y, multiplied by vector B dot y, and again add that to vector A dot z, multiplied by vector B dot z. And this can also be applied in 2D, so without z. But yeah, this is the dot product. Now, why is this useful and what does it do? So when I think about the dot product, I think of the shadow of a vector on top of the other vector. So with the dot product, we're dealing with two vectors. So let me draw two vectors here. And what the dot product does, as I said, is it's projecting the shadow of a vector onto another one. So what does this mean? So if I pick a yellow color, and if I draw a sun up here, you can see that the sun will cause this vector to cast a shadow on top of this one. And well, how does this work? Well, if you take this, the length of this vector as 0, and if this is 1, we're getting a value in between 0 and 1. And it could be, for example, 0.7 here. And here, 0.7 will be the dot product of these two vectors. Now, this is, as I said, very useful. So let's check out one of its use cases in the fragment shader. All right, so let's check out one of my favorite use cases of this function. So let's delete all of this and let's create a vec3, call it view direction. And this will be equals, okay, so Threejs also provides another uniform to us, and that is the camera position. So let's just put this at camera position and let's visualize this as a color. All right, so we have this uniform, Threejs provides it. We get this. If I change the view, you can see the color changes. Now I want the view direction in this case. So how can we find this view direction vector in a given point on our object? So let's go back to the drawing board here, and let's say I have a camera right here and I want to render the sphere. Now for this point, for example, we want to see what the view direction is. So this object is placed at a certain point. So let's just say it's centered at the origin of the world, 0, 0, 0. And so we have two vectors here. One is the camera position. If I draw it like this, we have one vector, which is the camera position. It goes from center to this position. And the other vector is this, the position of the vertex itself. So if I draw the vector of that, you're going to get this. Now, if I want a view vector, I need to subtract these two vectors from each other. And this will give me this part. But the problem is this vector could have a very big length or a very small length, but I just want the direction. So when you want to just know the direction of a vector, you normalize it. All right. So if we normalize this vector, we get our view direction. So let's implement that. So here I can do view direction equals camera position minus, and as I said, we need to subtract the position. So v position. And this gives us that vector that I talked about, but we need to normalize it because we want the direction only. So, and this way we get the view direction. Now, if I take a look at this, again, if I change the view, you can see this gives us this cool effect. Now, if I do this on a sphere, it would be much better. So let's change our object now to be a sphere. Let's do sphere geometry with a radius of 2. That's fine. And I think that works. That works for us. Maybe I need to increase the subdivisions. No, that's fine. Let's just keep it at 1. Yeah. And this is going to give us a sphere. We can rotate it. And for each point on the sphere, we're getting a different view direction, right? Now, what I can do with this view direction is I can take the dot product of this view direction with the normal of a point, and this gives me a very cool effect. So let's see what I'm talking about here. Again, remember the dot product gives us a float, so float, and I'm going to call this Fresnel because that's the effect that we're creating. This is the Fresnel effect. So we can do dot of this view direction and our v normal. So 2 vec3s, and this gives us the Fresnel. Now let's visualize what this looks like. We need to construct it as a vec3, and this gives us this spherical shape where we have 1 here at the center, and as we move to the edges we get 0, right? Now, if I can revert this, so if I revert this, this gives us the Fresnel effect, where we have 0 at the center, and as we move towards the edge, this gives us 1. And as I said, the dot product projects one vector onto another. And in most cases, what you need to do is you need to normalize these vectors to get the direction. Now, what the normalization does is the normalization sets the length of the vector to 1. All right. So if you use the length function on a normalized vector, you will get 1. Now, okay, so the dot product projects one vector onto another. How is this useful? Well, when you normalize two vectors, you can actually know if the direction is the same or not. And if the dot product is 1, you know the direction is exactly the same. If the dot product is 0, you know that these vectors are perpendicular. So here you get 1. Here, if I project this, I get 0, right? That makes sense. Now, what's happening here with our example is that the view direction is directly looking at the center point. And if I remove this for a second, what we will get is 1, because here at the center, the view direction is completely in the same direction as the normal. And as you move towards the edge, the direction of the normal changes because the surface orientation is now pointing this way, and the normal becomes perpendicular to the view direction, which is straight. And this gives you the dot product of 0 here at the edge. Now, if you invert this, for example, put 1 minus dot, this gives you the Fresnel effect. And we can type the Fresnel effect in Google. So if I go into images, the Fresnel effect is this effect where every object is dark in the center, and as it moves towards the edges, it becomes light. And you can use this effect to enhance your model's looks. So for example, here you have two images. one with Fresnel, one without Fresnel, and you can see the difference is night and day. Every natural object has Fresnel, and these are some of the functions that are available in GLSL. You also have the cross product, but we're not going to talk about that in this video. Just note that it's available. So now that we've figured out how these functions work, let's move on to drawing some interesting shapes. Alright guys, so here I have a list of things that we can draw. So the first item in my list is drawing a line. So let's remove all of these lines of code, very simple stuff, and let's change this back to a plane geometry because it's easier to draw stuff on a 2D plane. So let's use 1, 1, and that's it. We should get something, but I guess, okay, we're outputting Fresnel here. Let's do vuv.x. Okay, now let's increase the size of this, so 2, and we get this. All right, we go into the fragment here, and we want to draw a line. All right, so where can we start? Well, when we want a hard line, we probably need to use step, right? So we just keep that in mind. But how do we actually, how do we actually define a function that draws a line with a step for us? Well, something that I can think about is if I want to draw the line like this, here at the center, we should have more values that are close to 1. And here at the edges, we should have values that are close to 0. That way, I can step this and get a hard line. Let's see how we can do that. So the first thing I need is a function that makes this area 0. This is already 0, all right? And makes this area also 0. And here at the center, we want white, right? We want 1, right? So one thing I could do is playing around with this value. Let's subtract 0.5 here. So we get this, all right? The values are going from minus 0.5 here to 0.5. That makes sense. Now, I want a function that can actually, take this pattern and copy it on the other side, right? So here we have negative numbers. What if I could somehow copy this part onto this part? And from experience, I know a function does that. So if I come here and if we display the absolute value of x, this is exactly what we need. So the UVs go from 0 to 1, all right? That makes sense. But if we subtract 0.5, so if I subtract 0.5 here, this is going to move like this. And if I don't apply an abs, we're going to get exactly what we're getting. So we're getting minus 0.5 here. And when we go up to 1, we get 0.5. All right, so that makes sense. If I put an absolute value here, so if I do this, we're gonna get the absolute value, and this might look like something useful. So let's try this out. Let's see what happens. So if I go back to code, I can use an absolute value here. Now we can revert this. So let's come here and let's do this. 1 minus this. This will invert the whole thing. So we're getting a white line here, but it's smoothly transitioning into something here at the edge. Now, I don't care about that something. I can just step this and put the threshold, I don't know, 0.8. And we're going to get our hard line that we wanted from the beginning. So there we go. I can increase this and get a thinner line. So let's do 0.99. And we're going to get a very thin line. All right, so that's our first exercise. And the other thing I can do here is instead of vuv.x, we could do vuv.y. And this is going to give us a horizontal line, right? So, all right, that's done. The next item on my list is drawing a circle. Now, we already did this, so let's just copy this. And let's say line this, and okay. So we now want to draw a circle. So for a circle, we did try the length function earlier. So length of VUV itself, and we need to put this in a vec3. So come here and do that. So if you remember, we get 0 here and it goes like this. So we need to subtract 0.5 like this to make it go in the center, and we can step this to get our circle. So we can do step 0.5 or the U radius that we created earlier, and sorry about that, and we're gonna get this. All right, sweet. We can decrease and increase the value. But what if we want to do this another way? Let's explore and see what's possible. So I'm gonna copy paste this here. All right, so let's see if we can come up with another solution to this circle problem that we're trying to solve. All right, so let's copy this part again and let's see what we're trying to achieve. So another way to do this is, if you take a look at this, we have an origin point, and each and every pixel is drawing the distance to this origin, right? So if the distance is 0, we're getting 0, and as we're moving up, the distance is actually the factor that we're drawing here. So I can change this maybe to the distance function, but the distance needs to compare to some value. So if I create a const vec2 center, this is going to be the center of our circle. So I can do vec2 0. Let's put it as 0 for now, and let's compare the distance of the VUV coordinates to this 0 value. So let's just do distance of VUV to center, and we get the exact same thing, right? But this time we can actually modify the center to be in whatever position we want. So this is a nicer way to do things. Maybe we can come here and create a function, call it, I don't know, float, draw circle, and this takes a position, and we have a center. We can actually pass this in as a parameter too. So let's do position and vec2 center. All right, let's delete this, and we can return the distance of the position to the center, and we can return that. So here we can come and say draw circle. We're going to pass in the VUV as the position because it's the coordinates that we want to deal with. And here at the center, I can define anything, but let's do 0.5. And here we're going to get the exact same thing. All right, so we can do a step here, actually, to replicate what we had. Actually, let's do radius. Let's actually define radius here as well. And here we can pass in radius. So our radius can be U radius. All right, that makes sense. And we get this, and we can again control everything. And now this is a little bit different than what we did with this formula, but in terms of math, it's exactly the same thing. Now, this gives us a little bit more control over our parameters. And this is a fantastic opportunity for me to introduce you to signed distance fields. So I'm going to write it down, signed distance fields. And this function is essentially a signed distance field because for every position in our plane, in our world, in our 2D world, we're getting a distance. And if that distance is below 0, we know that we're inside the object. If that distance is 0, we know we are on the surface of the object. And if the distance is above 0, we know that we are outside of the object. Okay, that makes sense. Now, people have invented many different SDFs over the years. So we can search for SDF of a square. And the first site is from Inigo Quiles. So let's open that up. And if we scroll down, we can maybe find, yep, the SDF of a box. So let's copy that and let's put it here as the function. Now this takes the position. So this is the UV. So, and probably this vec2 is the size of the box. So let's copy paste this. So let's first, let me comment all of that. And we can come here and say SD box, and we can input the UVs. Okay, so that's our position on our plane, and here we can determine the size of the box. So let's set it to 1, and let's see what we get. And okay, we get a black box, so we need to put 0.5 here maybe. And there we go, we see something. Maybe we can offset our UVs to be at the center. And then we can maybe, again, drop this to 2.5. And again, we can maybe drop this to, I don't know, 0.15. So, yep, we're getting a box shape. And we can invert this to get white where there is a box. And okay, maybe we can use the step function here again. Let's use 0.9 and let's see what we get with this. And we get this. Okay, so there are many SDFs that we could use to draw different shapes and patterns, and this is just an example of that. Okay, so this opens up a whole set of opportunities for us to explore different functions that other people have invented. One particular function which is very interesting is Perlin noise, and I have the code of Perlin noise here. So let me just copy paste that here. All right, I'm gonna copy it and I'm gonna come down here and we're gonna comment all of this code, because it gets in our way. So let's just paste this implementation in, and this is a long function that does some crazy math. We're not going to get into what math this does, but this is called noise, and it takes a vec3. So if I come here and let's first of all save this, so let's delete and paste here. All right, and here you can use noise, and you need to provide a vec3. In this case, there are 2D noises too, but here I picked a vec3. So we can provide maybe the V position and get different noises at different values, and you get this, which is very interesting. Now, to scale this up, you can multiply this by a huge number, the V position, to get a better look at how this actually looks. And you're seeing some smooth noise here, right? So there are many videos made on the topic of Perlin noise, and we're not going to get into depth of what Perlin noise is, but definitely make sure to do your own research on this, because Perlin noise is very cool. Another version of this noise is simplex noise. And you see people using these noises to create smooth patterns and organic shapes. And in fact, in the final project in this video, we're going to create our smooth noise animation with this exact noise. All right, so next I want to show you how you can import images into your shaders. Now, let's comment this out. So I'm going to copy paste this here. Let's go into app.js, and here I'm going to create a new uniform. Let's enter this material.uniforms.uTexture. Okay, so we're going to be importing a texture, and we're going to be using the Threejs texture loader class. So new 3 texture loader. All right, and we're going to use the load function. So after initializing this texture loader, you can do load, and here at the top of this file I'm going to import an image. Now if you look at this repo here that we have, in the images folder, I have this image.jpg, which is this colorful image. Let's close that and let's try to import it. So here I'm gonna say import colorful texture from, and we're gonna do images image.jpg. All right, this is gonna import the texture, and we need to copy paste this into the load function here. So just copy paste that in, and here we added it to the JS side of things, but here we need to actually use it in the fragment shader. So you can go at the top of the file here, and you can use this as a uniform. So uniform sampler 2D, that's what you need to use for 2D textures. You're going to use sampler 2D, and the name of the texture is uTexture. So write that down, and all you have to do now is get the color of it. Now the function that you need to use here, so let's do vect for color, is texture 2D. All right, so texture 2D, and use the name uTexture, and you need to map this onto the object, right? And the UVs, UV coordinates are just made for this. So we're gonna use VUV semicolon here, and here we're gonna do color.xyz. All right, so that's all you need to do. And with this, if we reload the page, we're gonna get our image. Very beautiful stuff. Now I want to show you a really cool trick that you can do in the fragment shader with the dot product. Now this is another useful case of using the dot product. So I'm gonna paste this constant value here, desaturate, and this is a magical vec3. So what we're gonna do is let's actually change this to a vec3 color, and you can do swizzling here to store this XYZ. And let's delete this. So the dot product of the desaturate constant here and this color will give us a desaturated image. All right, so let's validate that statement that I just made. So we can do float final color and set this to the dot product of this desaturate constant and this color. And what the dot product here does is it actually gives us a weighted way of showing the brightness of the image. So you're gonna see what I mean by that. So let's just visualize this vec3 final color, and we will get this, which is pretty cool. We get the desaturated image. Now the way that this works is the dot product also in this case creates some weights for the color components. And the reason that this magical number works is that your eye is very sensitive to green, right? So green here has more weight, and after that is red, but it's not much, and after that is blue. So we're using different weights for each component of the color, and this final color gives us the desaturated image. And that's it for this section of the video. Next, we're going to be implementing the final project that I showed you in the beginning of the video. And I know this is a lot to take in. Definitely make sure to rest in between watching these sections. And of course, with more practice, you're going to get better, guys. All right. So I know I touched on a lot of different topics, and you don't really need to memorize these. All you have to do is practice, and you can just come back to this video whenever you feel like you just forgot something. All right, so that's it. Let's move on to the final project of this video. All right, so the project that we're going to be implementing is inspired by this artwork from Ducky 3D. Now, he has made a video tutorial on this, and all the credit goes to him, of course. So definitely like this video and subscribe to his channel as well. And what we're going to be doing is we're going to be taking a look at his process of making this in Blender. And we're going to take that process and translate it into a process that we're going to be using to create this in Three.js. Alright, so we're going to hop back into code, and we're going to be deleting these pieces of code. And I know a lot of you guys might be interested in keeping these. So what I'm going to do is I'm going to create a new terminal. I'm going to create a new branch. Git checkout -b, and we're gonna call this shapes. All right, so we're gonna do git add dot. This will add all the files, and we're gonna git commit -m save or something. All right, so I'm gonna be pushing this branch into our project repo, and you guys can check it out from there. So let's create another branch, git checkout -b, and let's call this organic. All right, so now what I'm gonna do is I'm gonna go through our shaders, and I'm gonna delete all the unnecessary code so that we can start from a basic shader from scratch. Alright, so now what I have in my vertex shader is very simple. We have this uniform float utime, which we update in our animation loop, and we have these three variants: v position, v normal, v uv, and we set them here, and we have the MVP model view projection matrices math, and that's basically it. In our fragment shader, we're just having the same thing, so uniform float utime, our varyings, and we're just outputting a simple red color. Now in our app.js, what I'm doing is I'm just setting this uniform utime to this object with the value of 0 at the beginning, and as I said in our animation loop here, we're gonna come and we're gonna update this. So we're gonna do material dot uniforms dot utime, and what I'm gonna do is I'm gonna set the value to the timestamp. All right, so now this might be a little bit too much, so let's do time equals timestamp, and let's divide this by 1000, and let's do that. So with that, we have our basic setup here, and with this you're gonna get this red plane. Alright, so what I'm gonna do now is I'm gonna come to this video, and we're gonna try to replicate the process of this. So first, I'm gonna try to create the pattern on a plane. So the first pattern that we're gonna see in this video is this stripe-like pattern with these lines, and we already covered this. This is very easy to do. So what I'm gonna do is I'm gonna do this in the fragment shader, and we're gonna create a vec2, call it UV, and store VUV in it so that we can modify the UVs. And if I remember correctly, we're gonna be using a fract. So let's just do fract, and let's just put the UVs in here. And what I'm gonna do is I'm gonna just take the uv.x, and of course this is not going to work because the uv.x is always between 0 and 1, and we need to multiply this by a value like 10. And with this, this should work. Now we need to wrap this in a vec3, so let's do that, and let's see the pattern that we get. And yeah, we get this stripe-like pattern. Now the problem is we're getting this gradient almost here. So what I'm gonna try to do is I'm gonna try to use a step on this to get rid of that gradient, and we can have some hard edges here, right? So yeah, we get the pattern that we need. Now let's apply this on a sphere, because this is applied on a sphere. So let's go ahead and change this geometry that we have to a sphere geometry. Let's set the radius at 1, and we're gonna get this, which is pretty cool, but it's not what we want, because this is like not going from top to bottom. It's kind of going from side to side. So maybe what we need to do is use the uv.y, and let's see what we will get with this. Okay, this is interesting. We're getting something very similar to the video here. And the next thing that Ducky 3D does is he loops this with an animation from side to side. So that's what we're going to be doing next. So let's come here and let's change this uv.y, and let's add utime here. And we're going to get our animation. Now it's a little bit too fast, so let's again add another 0 here, and yeah, we get our smooth slow animation. All right, so next what he does is he makes this pattern smooth. Now there are many ways to do this, but one quick way that I thought we can do this is actually if we come back here, we're using a fract. Let's not do that. Let's use a mod because we want to be able to control the space between our lines. So what I'm gonna do is I'm gonna come here and say mod 1. Now this is gonna give us the exact same result. Don't forget to make this a float as always, and this is gonna give us the exact same result. But now what we can do here is we can search for a smooth mod function, and this hopefully will smooth out our pattern like here. Now let's see if that thing exists. So I can do smooth mod GLSL, and it looks like we have something. So let's click on this website. I'm gonna scroll down and I'm gonna copy paste this code. So let's also copy paste the comments above it. And I'm gonna come here and paste this in. So smooth mod by this guy. All right, and let's take a look. It has some documentation as well. So we first have an axis, so input axis to modify, and we have an amplitude of each edge or tip. We have a radius for each edge or tip, and it returns the smooth edges. All right, so that makes sense. Let's come here and try this out. Let's use this instead of the mod that we're gonna be using. All right, so now this seems like what we already have here, the amplitude, but the radius we can actually change. So I'm gonna put the radius at 1. And let's see what we will get with this function. So we get nothing. Let's check why that is. So if I open up the console, you're gonna see this line. Pi is undeclared identifier, so pi doesn't exist. So we need to actually define this pi value that this introduced. All right, so here might be a good opportunity for me to introduce you to macros in GLSL. So we can do define, hash define, and this defines a macro in GLSL. All right, and a macro is simply if you put pi here, and if we put 3.14 like this, we can actually replace parts of the code with this macro, and at compile time it's going to replace the whole macro with this parameter that we provide. And what that means here is that we're using this pi variable here, and at compile time it's just gonna put this at 3.14. and macros are of course not variables. The difference between macros and variables is that the macros are always defined at compile time and not at runtime. So we're gonna put pi back here, and what I'm gonna do is I'm gonna replace this part with a pi value with more precision. All right, so I'm gonna paste this in. This has more precision, and you don't have to put a semicolon here, because if you put a semicolon here, it will replace pi with a semicolon. So you will get 3.14 with a semicolon after it, and that of course leads into errors. So you shouldn't really put a semicolon there. So yeah, we're gonna get this. Now this is the exact same result. This isn't smoothing anything, so maybe we need to change the parameters here. My guess is that we need to now get rid of this step function, because the mod function already does the smoothing for us. So we can just remove that, and we're gonna get this, which is pretty cool. Alright, so I experimented with some parameters, and what worked for me was this. So change this to 1.5, this radius parameter, and what you need to do is actually set this to a higher value. So if we set this to a higher value, you're gonna get more lines, very similar to this one. But this still looks off a little bit. So what we can do to make it look like this is we can scale these values to fit in a certain range. This is already smooth, but we want these values to fit in a certain range, right? So what I'm gonna be doing is I'm gonna go back into code, and I'm gonna use a function that I pretty much always use in my projects, And this is a math function, so let me just copy paste it here. So here I'm going to paste this. This is the fit function, which I always use to fit certain values in certain ranges to another range, right? And this essentially scales it. So we have this unscaled, and we have this original min, original max, and a min allowed and max allowed. All right, so let's take a quick look at this, and the values that we're getting are kind of like similar to each other, and it looks like this is going from something like 0.2 to all the way to 0.7 or something like that. So let's copy this entire thing and let's put it in a vec3 variable. Vec3 color equals this, and what we can do is actually we need to take this as a float, and let's call it pattern, and let's put pattern here. All right, this should work the same as before, and what we can do is now fit this into the range that we need. So as I said, the original min and max might be something like 0.2 and 0.7, so that's the original range, and the range that we really want is 0 and 1. So this is gonna scale this to fit this range. So as you can see, that worked somewhat. Let's also set this to 0.3. Let's see how that works. Okay, we get more dark areas like this, and also let's change this to, I don't know, 0.6. Let's see the effect that that has, and yeah, this is starting to look exactly like this. All right, so with the values that I experimented with while I was preparing this video, I came to these values. So let's change this to 0.35, and this should be 0.6. That works nicely, and we get this pattern which is extremely similar to this. And let's now move forward. All right, so the next thing that he does is he plugs this noise texture thing as a vector into the wave texture or the wave node here. So we already kind of have this wave node. We can maybe make a new function, call it, I don't know, float wave, and it takes a variable, a vec2 called position. This is normally what I call my variables. So let's take this and let's put it here. Let's return this. So instead of UVs here, I'm gonna do position.y, and this should work fine. So we have this wave function. All right, so let's come down here and do float pattern equals wave, and let's pass the UVs in, and this is essentially going to give us the exact same thing. All right, so what we can do now is we can plug a noise texture into this UV, but how do we actually do that? So first let's copy paste the Perlin noise implementation, which I showed you guys earlier. All right, so let's come up here and let's paste this in, classic Perlin 3D noise by Stefan Gustafsson. All right, so, and this gives us this noise function, which takes a vec3, and the reason I'm using the 3D version of the Perlin noise is because we're dealing with a 3D sphere, right? And for 3D objects, I always use the 3D Perlin noise. And all right, so let's copy this. Let's come down here and let's see how we can deal with this. So I think the name here is a bit confusing. So let's change this UV name. First of all, the thing here is this UV is actually a vec2, but our Perlin noise function needs a vec3. So the way that we can fix this is instead of using the UVs, we can use the normals. All right, so we can do normal, and the normals are vec3 if you remember. Now let's change this parameter name into something better. What I'm gonna do is I'm gonna name this chords or coordinates. All right, so You can also call it position, but I'm gonna call it chords. So this should be a vec3 now. And also this is gonna break because this takes a vec2. Let's change that to take a vec3. And with this, everything should work the same as before. We even get more lines. So what we did here, we should change this to something like 6 or something. And yeah, we're gonna get the exact same thing, but now with the normals. All right. So if you take a look at what Ducky 3D does, Ducky 3D uses the noise texture as the input for this wave texture. All right. So we need to somehow change this chords to do something, right? So what we can do to change this chords variable is we can do chords plus equals, and we can distort this with a noise. So let's do plus equals noise maybe, and let's use the chords as the input. So we're gonna get this, and this is the exact same thing that we want. Now the problem is you're gonna see these weird lines here, and this is because we don't have enough subdivisions in our sphere. So I'm gonna come here and let's also change this sphere geometry to an icosahedron geometry. That gives us a better spherical shape. So let's put the radius at 1, and let's set the detail at, I don't know, 50, for example. And yep, we're gonna get the exact same thing because the math is exactly the same. So let's rename this to something else. Let's do vec3. Let's call it noise pattern. All right, and we're gonna make this like this, and we can pass this noise pattern into this. All right, so everything now is nice and clean. Now we're getting this shape, and let's move on with the tutorial. If we continue, again, we have the exact same setup here. The next part is displacement. All right, so far we've kind of been in the fragment shader, and we've kind of played around with the values, and we kind of got this to look the way that we want it to. But next we want to do actually some displacement with the geometry. And as you guessed, we need to now move this algorithm to the vertex shader. All right, so let's copy all of this code, and we're gonna move everything to the vertex shader. All right, so we're gonna come here, and here let's put a comment here stating that this is the varying section. And all right, here I'm gonna paste all of this code. Let's move all of these lines like this. Now of course, here in the vertex shader, we don't need to use the v-normal. We can actually use the normal, and everything else should be fine. Now we need to take these functions, and let's go up to this point. Let's copy everything here. Let's paste all of this code in. All right, so this should give us a normal sphere, and everything should compile fine. Of course, I need to set a value here. Let's actually create another varying. It can be a vec3, but let's do float, varying float v displacement. All right, so we're gonna copy this, and we're gonna come down here, paste this in. And v displacement can be equals to this pattern that we have. So we can have our pattern here. Actually, let's move all of this code above everything else. So we have our main function here, and we set the varyings, all right, like this in one place. And let's put a semicolon here. And here what we can do is we can output this output this as a vec3. So let's paste that in, and we're gonna get this. Now the reason you're seeing this issue is because our vertex shader now is responsible for creating this pattern, and the number of vertices are much lower than the number of pixels that we were dealing with before. So what we can do here is we're going to come into our code and in app.js. Let's change this to 100, and you can see this fixes the issue because we now have much more vertices, and those are handling the pattern nicely. All right, so let's go back here, and now what we're gonna do is we're gonna displace this. So for this, let's go back to the drawing board. Okay, so here we want to displace this sphere, and the result that we're looking for is something like this, where we apply the noise to the surface of the sphere, and we should be able to get something like this orange outline at the end, right? All right, so here what we want to do is we want to elevate each vertex to reach this position, right? So we want to elevate this to reach this displacement, right? And the only thing we need for this displacement and changing the position is first we need a direction. So we need to know in what direction we're going to be pushing this vertex in, right? So our vertex is going to go from here to here, and the direction here is important, right? So that's the first thing. The second thing is how much are we going to push this vertex in that direction? So these are the two questions that we need to answer here. Okay, so the first question is what direction should we use for each vertex? And if I draw each vertex direction that we want all around the sphere, you're gonna see a pattern showing here, right? So if we draw this part where the direction goes inside the sphere, and this part, they are all gonna reach one single point. So like this, like this, like this, like this, and this point is the center of the sphere, right? So the direction here is the direction of a vector that goes from the center to the vertex on the surface, right? And in this case, the direction is actually the normal of our sphere. All right, so the normal gives us the surface orientation, and it's a vec3. And in this case, it also gives us the direction that we need to be pushing these vertices in, right? So that's the first question. We need to use the normal to define the direction, right? And the normal is already normalized, so you already know that the normal gives you a direction and an orientation, right? The second thing that we need is how much should we push these vertices along this normal direction, right? So the answer to that is we need to push these vertices by the noise factor, right? So if we want to get this noisy shape, we need to, when the noise factor is higher for some vertices, we need to push it higher along this normal direction. So let's implement that very quickly here. All right, so what I'm going to do here is I'm going to come into this vertex here, and I'm going to create a new variable, call it new position. All right. And again, we need two factors, right? We first need the direction that we should push the vertex in. So that's going to be the normal. And how much should we push that vertex in that direction? The answer to that is our pattern here. Or we can use the v displacement because we're already assigning that to the pattern. All right, so just to keep it clean, we're going to use the v displacement. And let's check this. Let's see if this is working or not. So let's paste this in, and let's go into here. And yes, we are able to displace our sphere like this. Now, there are multiple problems here, of course. One is this jagged edge, which we're going to fix later. But the other one is our displacement is starting from the center point here, right? And this gives us a bit of a weird look, right? So if you take a look at the displacement that Ducky 3D has, if we go back here in the beginning, the displacement that he has is very subtle, right? It doesn't start from the center of the sphere. So the way that we're going to be able to fix this is we can come here, and here in this position, we can actually add all of this to the existing position. Now this way, we're taking the position that the vertex is already in, and we're pushing it along the normal by some value. All right, and that's gonna give us a much better result. And this is gonna give us this result. Now, this again has too much displacement in it, right? So we need to maybe turn this a little bit down. So I'm gonna come here and call this float displacement, and take this V displacement divided by 3, and use the displacement here. And this is gonna give us this result, which is pretty nice. Now, we still have these jagged edges here, right? Now, the way to fix that is again going here and increasing the detail amount in the icosahedron. So if I increase this to 200, you're not going to see those jagged edges anymore, right? But this is gonna slow us down a bit when we want to reload the page. So I'm gonna turn this back at 100. All right, so we're gonna get this jagged edges, but that's fine. And we're gonna get these jagged edges again, but it's fine. So let's come back here and let's take a look at this. All right, so we want to achieve this now. Now Ducky 3D doesn't do anything special after this point. Of course, the lighting process is a bit different in Blender. So we need to achieve this section, this part on our own. All right, so let's take a look at this and let's see what's the problem. So the first thing is we don't want to be displaying the displacement values as the color. That's the first problem, because here Ducky 3D is using a solid color for all of this, right? So we're gonna come here and we're gonna set this to a solid color. So let's use blue because why not? So I'm gonna put these values like this, and let's see what we will get with these values. And we get a solid color, but the problem is we don't have any shadows, we don't have any lighting, we have nothing here, right? And that's very sad and boring, right? So the obvious thing here is that we're not going to write this whole fragment shader for lighting and shadows today, because that would take the whole day. And the way that we're going to do this is we're going to inject our own shader code into Three.js materials. And now I have a full video on this explaining this topic. So you should go ahead and watch that video first. And if you already know how to do this, let's just begin. So I'm going to come here and I'm going to replace this with a mesh standard material. And this code will no longer work. So let's just delete that. And the way that we're going to be doing this is with the onBeforeCompile function. So onBeforeCompile, and this gives us a shader, and we can store this shader in the user data of the material. Again, all of this is in my tutorial on how to inject your shaders into Three.js materials. So we're going to do that, and I'm going to copy this right here. And instead of doing material.uniforms, I'm going to do shader.uniforms. All right. So this is storing a reference to the shader object. And this is uniforms. All right. So the way that we're going to be doing this is by first, let's console.log the vertex shader, because most of our code happens in the vertex shader. So let's do shader.vertex shader, and let's see what we will get in the console. So first, we're gonna get this error, of course, in here. So now the way that we're gonna be doing this is with material.userdata.shader. All right. So now we get the string, which is the vertex shader. And now we need to actually look for parsing vertex shader. And now we have to actually divide the vertex shader that we have into two different parts. One is the parse and one is the main section. So let's do the parsing one first. Let's copy this, this include, which has the displacement map parse vertex. And we're going to come here and we're going to say shader dot vertex shader equals shader dot vertex shader dot replace. And the way that we're going to be replacing this is we're going to come here and define a parse vertex string. So let's just paste that in, and let's do this, paste this in. And here, if I add a comment, if I add GLSL behind this and comment this with Shift Alt A, I'm gonna get syntax highlighting for GLSL inside JavaScript. And the way that you're gonna get that is with this extension called GLSL literal. All right, so let's just type that in, and syntax highlighting for GLSL inside of JavaScript tagged template strings. So you can download this and install it. And if you add a comment like this before any GLSL string, it will add syntax highlighting for you. All right, so here what I'm gonna do is I'm gonna use the replace, and we're gonna pass this in. So parse vertex string, and again I'm gonna come here, and what I'm gonna do now is I'm gonna use the same string, so parse vertex strings, but here I'm gonna add our own vertex shader that we need. So here I'm gonna do vertex shader parse, and we need to create a new file here in the shaders folder. Let's add vertex parse.glsl. all right, and what we're gonna do here is we're gonna copy all of these uniforms varying functions that are at the top of the main file. All right, so all of this code we're gonna copy, and we're gonna paste it in here, right? So that's it. We now need to import this section, so we can come here and say import vertex parse shader parse, and from /shaders vertex parse. All right, and let's change the name of this to vertex parse as well, because that is much nicer. And we need to now define a vertex main, so vertex main, and we need to now create a file called vertex main. So again, in our shaders folder, create a new file, vertex main.glsl. And here we're going to copy and paste the contents of the main function of our vertex shader. And you only need to copy up to this point, because the vertex shader in Three.js already does this MVP calculation stuff. So all you need to do is you need to copy this part, right, into the vertex main, paste it here. And now what we're going to do is very simple. We're going to come here in our app.js, and we added this vertex parse here, and we still have this string. And now you're going to get an error here because you're redefining pi and v normal and stuff like that. So what you can do is just come here and into the parse section and just delete this. Delete v normal, delete vuv, delete position, keep the displacement and utime, and you also need to delete the define pi because Threejs automatically defines pi. And with that, you're gonna get no errors, right? And here we can see our code that has been replaced, but we're not gonna care about that. We're gonna come down here and find another displacement include, which is now in the main function. So we're going to copy this displacement map vertex, and here in app.js, we're going to create const main vertex string. All right, and again, the same thing. We're going to create a literal template literal and paste that in. And again, the same thing needs to be applied here. So shader.vertex shader equals shader. Let's actually close this because it's taking up space. Let's continue. So vertex shader dot replace. All right, and we're going to use this main vertex string. And again, we're going to use this main vertex strings plus we now need to use the main vertex thing that we have. So here we need use the vertex parse. Here we need to use vertex main, which comes from our file. So here, if I go here, this comes from our file here, right? And with this, everything should work fine so far. Let's see what error are we getting. So we have a vPosition undeclared identifier. All right. We have a VUV, which is undeclared and stuff like that. So here in the main, we need to actually delete these varings that we had because we only now need the V displacement. Let's also format this properly. Everything should work fine now. Yep. We get no errors. And now we need to actually displace this sphere, right? And here in vertex main.glsl, we're going to modify this transformed variable. Now, if you're interested in where did this variable came from, we can go into node modules, scroll down to find 3. So here, 3, and open up the src folder, open up renderers, open up shaders, and open up shaderchunk.js. All right, so we can close this now. And if we search here for displacement, this is the file that we're actually replacing in Threejs. If we open this up, displacement map vertex, we're gonna get this code. Now this is very interesting because we can actually see how Threejs handles the displacement based on the displacement map, right? So we have this transformed, and Threejs adds this part to this transformed variable, which is very similar to what we wrote. So we have the normalize object normal, which is the normal of the object, and we multiply that by the value that we're getting from the texture, which makes sense. And it has also other parameters, but here you can see a structure that is very similar to our code. So what we're going to do is we're going to use this transformed, and this is a vec3. So we're going to come here into vertex main.glsl, and we're going to add equals, all right, normal. So we have the normal. We can actually in this vertex here, it seems like Threejs is doing this. So maybe we need to actually copy this and use it as the normal. So let's do that. Let's multiply this by the displacement value, and this should give us the displacement that we want, right? So yeah, this gives us a custom shader that does the displacement for us. So if I went a little bit too fast here, here's the code that you actually need to be writing in the Umber4 compile and in the material. This is the actual code that you need to be writing. And to access this shader, you use the material user data, right? So very simple stuff. I already explained all of this in my other tutorial about injecting your shaders. And now this looks a little bit weird. And the reason for that is we haven't actually done anything with the fragment here. So if you take a look at this, this not only has displacement, but this object also has bump. So it actually looks like that between the edges here, we get some lighting effects and shadows. And that is actually what bump does. So we need to now go into here, and we need to modify our fragment shader as well. So what we can do here is we can create 2 other files in the shaders folder. One should be fragment main.glsl, and the other one should be fragment parse.glsl. And this is how we handle things. Let's close these unnecessary files here. We're gonna need the shader chunk file later, so let's keep that. Put it at the very end here. And what we're gonna do is we're gonna look for the displacement or bump in our fragment shader. So if you take a look, we have this bump map parse fragment. All right, let's open that up. It defines some functions here. All right, so if you take a closer look at this bump map parse fragment.glsl file, you're gonna see we have two functions here, and we have some references here also. But if we go back into shaderchunk.js and search for bump map or bump alone, you're gonna see we only have this bump map parse fragment in the entire file. And what this means here is that these functions are being used in other files with other names. So how can we find these functions and where they're being used? So you can select it and press Ctrl+Shift+F, and this is gonna search for you in the entire repository. And when you search for this, you're gonna get this file, which is the normal maps fragment shader. So let's again close this, and you can clearly see here how this is being used to add the bump map, right? So here we can copy this part into our fragment.glsl, not this one, but fragment main.glsl. And now let's paste this in. All right, so we have this line of code, and now let's inject this. So if I come here and console.log shader.fragment shader, if we open up the console, we're gonna get our fragment shader here. All right, and now we need to find the parts that this happens, this normal fragment part. So we need to copy this part, normal fragment maps. If we come here, let's search for that, normal fragment maps. Here it is. Let's copy that, and let's go back into code, app.js. And what we're gonna do is we're gonna store this as a string. So main fragment string equals GLSL, comment this, and with this you're gonna get this. So that's it, and let's do shader.fragment shader equals shader.fragment shader, replace, and main fragment string, and we're gonna replace this with main fragment string plus the file that we're gonna be importing, which will be fragment main. All right, so let's define that at the very top here. So we're gonna do fragment main and also a fragment parse, right? And let's change this to fragment. All right, and now what happens is, well, we need to actually define this fragment parse as well. So if we come here, and I can do the same thing for the parse. So shader.fragment shader equals shader.fragment shader dot replace. So let's go back here and see what we need to actually replace. So what we want to replace this with is the bump map parse fragment. So let's search for that. I think we have the string here. So if I look through these, bump map parse fragment, we're gonna find it here. Let's copy that, and let's go to app.js. Let's store this in const parse fragment string equals GLSL, comment this, paste this in, and parse fragment string. All right, and again here, come down below, parse fragment strings plus parse or fragment parse, and let's format this. This is much nicer now. So here we need to actually copy paste the parts from the fragment shader. So going to fragment.glsl, and what we need to paste is we need to copy these two lines actually. So only these two. and we can go to fragment parse.glsl, paste this in, and that should be it, right? This should work. Let's check the console. Nope. Alright, so after 10 minutes of debugging this issue, I realized that here in app.js at the very top, where we defined fragment parse, we made a typo here. So let's change this back to fragment parse.glsl, and this fixes that issue. But we still get an error here, and I expect this error because let's look at what it's saying. It says this function doesn't exist, this function doesn't exist, and the reason for this is if you take a look at Threejs' code here where we define these functions, it has an if-def here, and if-def means if this define exists, you can compile this code, and this will be in the final compiled code, right? If this define doesn't exist, then you just don't define this code, right? And so these two functions aren't actually defined. But here's the problem. The first problem is this function is using a bump map, right? So if we go above here, we can see the bump map being imported here. Now we don't have a bump map. The thing that we want to use as a bump map is our noise variable or our noise pattern. Okay, so we don't need to import this function actually. So the only thing we need here is we need this function only. So let's copy this. All right, let's go into fragment.parse.glsl, and here we can paste this in. Now let's format this as well, so we can do this, and we now need to use this. All right, so here in fragment main, we're using this function, which seems to create bumps, and we're also using this function which I showed you, which uses a bump map. Now if you take a look at the name of this function, dhdxy, and if you take a look at the implementation, this is actually calculating the derivative of a point based on the height map or the bump map in this case, right? So that's what we're going to be doing, but instead of having an image as the bump map, we're going to be using our own noise variable, right? So here in the fragment parse.glsl, we don't have to do anything, but here you can see we have this function here, which I haven't really talked about, dfdx and dfdy. So these calculate the derivatives in GLSL. So I can come here, and instead of having this, I can delete this code and create a vec2. One should be df dx of our v displacement. Remember, we're importing v displacement as a variant here. So v displacement, and the other component should be df dy of v displacement, and this should work fine. So let's reload the page, and yep, we're getting something here. And now this looks very weird. This looks like it has flat shading actually. The problem here is we're actually calculating the bumps correctly, but the issue here is that we don't have enough segments in our sphere, right? So we can go into app.js, and now we can increase the resolution to something like 300 detail. And when we do that and reload the page, we're gonna get this smooth result, right? And that's basically it. That's the main section of this whole shader, and it nicely animates. Now what you can do here is you can actually increase this even further, make it 400, and this will give you a much better result. So the next part here that we need to implement is, again, if you take a look at this, we have some nice coloring here. So we can actually do some coloring, but I'm not going to do the coloring on the mesh or on the material. What I'm gonna do is I'm gonna do some lighting, and we're gonna do some post-processing to make this look cool. So here in app.js, I'm gonna scroll up, And here in the lighting section, I'm gonna replace this part with some lights, and I'm gonna change the color, change the position of the light. So I'm gonna give you a second to copy this part. This is the lighting setup that we're gonna be using, and let's do some post-processing now. So at the top of the file, I'm gonna import a post-processing pass, which is the Unreal Balloon pass. All right. So we're gonna scroll down now, and here we can do some post-processing, and these are the passes from my boilerplate code. We don't need them. We can just remove them. So we can do post-processing and add pass. This is a function in my template. So add pass, and let's construct a new Unreal Balloon pass. So I'm going to paste this in with some parameters, and again, you can have a look at this and copy this yourself. Set the intensity to 0.7 here, the radius to 0.4, and the threshold to 0.4. And this will give you this final result. Now this is the final result, which definitely looks cool. Now here are some adjustments which you can make to make this even look cooler. So here at the timestamp, I'm gonna remove one of the zeros to make this move faster. And once we do that, we get this animation. Now our noise function scale is kind of high, so let's just go into our vertex main, and here where we create the noise, let's divide chords by 1.5. all right. Now another thing you can do to make this look even cooler is add U-time to the input of the wave function here, right? So you can do that, but this will look a little bit too fast. So what you need to do is go into app.js, and maybe we can set this to 5,000, and this will now give you our final result, which looks very cool, very organic. And that's it for this crash course, guys. I hope you enjoyed this video. Of course, there are many things that we could have covered in this video, but don't worry, there are going to be more videos coming out soon about shaders. And big thanks to Ducky 3D for his amazing artwork. Definitely subscribe to his channel as well. And I would like to thank Bruno Simon for his amazing Threejs journey course. And I definitely started out learning shaders from his course. And I really hope that this tutorial has helped you become much better at shaders. And of course, when you're a beginner, shaders can be very hard to work with. Don't be discouraged. Just keep going, keep moving forward, keep learning new things. And you know, in some parts of this tutorial, I might have went a little bit too fast, but I wanted to really show you guys what's the possibilities behind shaders and how you can create really amazing stuff with shaders. So that's gonna be it for today. Thank you all very much for watching, and on that note, I'll see you guys next time.